Yeah, so I think we are live now. Okay, so I'll just share my screen and to learn and explore further on AVL Trees. Uh, please ignore, I know it's hard to ignore, but do ignore the latency. I'm having issues with my Wi Fi. Maybe, uh, maybe if I turn off the video, will that increase my chances or decrease? Okay, so how do I turn off the video? Edit to the so I think I saw something. So let's do video somewhere. It's not made for kids. But can no. Standard YouTube license. No, I don't think there's. What's under customization? Anyways, I think we don't have an option for turning off the camera. So I'll just quickly erase what's not required. Maybe this thing as well. And as usual, I was just learning the theory part. So I hope my screen is visible. Yeah, it's visible. So basically, what is an AVL tree? Just imagine AVL tree is nothing but a binary search tree whose left subtree and right subtree should have the absolute difference in their heights to be 0 to 1. Now, what I mean by absolute is the delta between the left or right or left should be 0 to 1. If you don't take absolute, then basically the factor should be between minus 1 to 1, which is obvious. So in an AVL tree, so it's a self-balancing tree. If I insert certain numbers, and if either of the branches go, um, either of the branches tend to increase, then the uh, AVL trees feature allows the branch going extensively increasing manner to self-adjust and redistribute the nodes among the other branches. So let's suppose, for example, this is an AVL tree, and so um, right now this is a balanced balanced binary search tree. So, for example, if I insert one more node, let's take this for example, then it's not a balanced binary search tree. So, eventually, we'll have to do some sequence of steps in order to balance it. Now, by balance, what I mean is the the balance factor, which is again the left subtree's height minus the right subtree's height, should be between minus 1 to 1. So either of the subtrees should have their height only differ by 1, which in this case is not the scenario. Which in this case it's not the scenario. So you see here that the height of this particular subtree is 4. For this it is 3. Or is it? It's 2. So 4 minus 2, it's 2, which is not the ideal case for AVL. We have defined, or as I should say, there have been defined some methods to make to balance this binary search tree. Now these contain some sorts of rotations. So first one is left left rotation, right right rotation, left right rotation, and right left rotation. So uh, so we can always go through the theory. I'm not going to focus on theory for now. I already have went through it. Applications and advantages you can read, and there are some disadvantages as compared to red black tea, which we'll explore further after we do the insertion. Okay. Now let's spend some time on the insertion. Okay, which is sure thing. Um, we can read the section. The idea is to use recursive BST instead of transition. We get pointers to all ancestors one by one in a bottom-up manner. So we don't need a parent pointer to travel up. The recursive code itself travels up and visits all the ancestors of the newly inserted node. So what the algorithm says is perform the normal BST insertion. Now, uh, what is BST insertion? Normal BST insertion is nothing but you try to fit the node where it should belong. So let's say there's a binary search tree, uh, root node, less than root node, greater than root node. You have given some value that you have to insert as a node. Let's say k. You compare here first root node. K is greater than root. You go to right part. K is less than the uh, right of the root. So it will come to left of this node. So what you do is create a new node and uh, recursively go to the node where it actually fits and give that particular node the reference of the newly created node. So in this case, root uh, dot right, not root dot right. If we consider the root dot right as node, the node dot left is equals to newly created node. So this will be your BST insertion. The current node must be one of the ancestors of the newly inserted node. Current node must be one of the ancestors of the newly inserted node. What do you mean by this? Current node must be one of the ancestors with the height of the current node. Okay. The I'm confused about this one. Get the balance factor. Uh, okay, did we come to this conclusion? So, as we have discussed earlier, what is the balance factor? It's nothing but left subtree's height minus right subtree's height. In this case, it's greater than 1. So that left subtree must be right. So to balance left subtree, we have two rotations: left left and left right case. So that's where the conclusion is arrived. That's how it is happened. To check whether it is to further bifurcate, compare the newly inserted key with the key in the left subtree root. I think my laptop is running. Let's check the temperature. Oh my goodness, 70, 99. Holy heck. We'll just check quickly what is the feedback. AVL. Okay. Anyways, we'll just use sure. What? Don't we have debug already? Oh, I think we'll just launch. Okay. Anyways, let's focus on this thing again. So, if balance factor is greater than 1, we check this one. So, compare the newly inserted key with the key in the left subtree. Okay, understood. If the balance factor is less than -1, then the current node is unbalanced. We are either in the right case or right left case. Again, the same process is followed here. So what we do is we'll first create a node. This is how the node class will be. So let's just follow the node class, shall we? Okay, so node and height. So we have instead of key we'll say val. We'll have a node left. I think node is the class itself. Okay, so what we'll do is we'll just uh, create a static class maybe. Left node right, then we'll have node. It's a okay parameterized constructor. So we'll have okay. So this dot val and this to val. Then we'll have height equals to 1. Okay, I think that's it. And I think we should initialize left equals to null, right equals to null. Are we doing this? We're just referring it to something. So this is the node. What does this say? Okay, make it static. We'll do it later. Let's just implement a class with let's say AVL operations. Okay, the AVL operations. What we'll do is from insertion perform deletion. These two things will try to perform. what happens is we'll just first straight away declare the utility functions. Basically, we have the I hope my screen is visible. Let me check. Oh, yes, it is visible. So, okay, so we're not returning that. We just return n dot.